Hello everyone, and in this lecture we'll study what is union find and especially disjoint data structure. But before we begin, let me acknowledge the source of these slides, and I've got this presentation from Robert Sedgwick, professor of the Princeton course, and let me acknowledge that all the materials I found from there, and they have a license about that. So yeah, let me begin. And first of all, union find. And in this lecture, we'll study what is dynamic connectivity, what does it mean, how to apply it, and quick find, quick union, which are two basic algorithms for, application of all this union and find, and some improvements. So given these algorithms, how can we improve them in terms of space and time? We'll study this also, and actually the basis of all these studies is how to apply it, and in this lecture we will study how to apply them. Yeah, but in more depth we'll cover it in these lectures, so be patient. So first of all, let me start with the subtext of today's lecture and this course. So what does it mean is what kind of philosophy we will use to actually solve the problems on all the topics which we'll cover. So first of all, what are the steps of developing a usable algorithm? So what does it mean that it's usable? It means that it's very convenient to use and it can be applied in a variety of situations. It's robust without any errors and have some practical application for the task which we've got. And the philosophy is that first of all we have to model the problem. So we have some description of the problem. Maybe we need to find some, maybe there is some context about some, I don't know, some history or some situation which we are in the problem. We have to model it in terms of input and output in order to decrease the number of details in the problem. And the second one is find an algorithm to solve it. So we have the problem, and not all the algorithms are suited to solve it, and we have to we have to select out of all the algorithms the one which works in this case, or we have to develop it on our own. So, and the third question we have to ask is this algorithm which we've chose to our problem and solve it, is it fast enough? I mean, in terms of time complexity, how many hours, how many operations does it consume? Or if it fits in memory, does it mean that if we optimize in terms of time, it's always optimized in terms of memory? Not, we have to also consider the memory, how many memory it consumes. So for instance, if we create some additional array, we see whether this array is actually contributing to the problem. If we created some additional auxiliary array, it consumes n space, but we'll cover what it means in the future lectures, and this force is not figure out why not. So if your algorithm is not fast enough, you have to find some causes why it's not fast in order to find a way to address the problem. So finding the cause after you found it, you actually know how to address this problem, or you can create some strategy. And the last one, iterate until satisfied. So you iterate all the steps, model the problem, find an algorithm to solve it, and so on, until you are satisfied with the solution, or if you interview, until interviewer are satisfied with your solution. It's all about the scientific method. So here we use science, and it's not some pseudoscience, it's actually the way of, for instance, how research papers are developed in almost similar way, but here you use science to actually solve the problem which are given. And actually the third backbone of this subtext is mathematical analysis. So we have to do mathematical analysis in order to, for instance, tell more about is the algorithm fast enough or not, does it fit in memory, and especially it's about time complexity of the algorithm. So let's move on. So let's start for dynamic connectivity, and in the dynamic connectivity problem we have a set of n objects and we have to support u operations, how to connect your objects, and to answer the question, is there a path connecting the two objects? So here we have 10 objects starting from 0, and we can connect them 4 and 3. For instance, when we connect 4 and 3, there is edge between them. And after we've connected all this stuff, we can actually say whether, for instance, 0 and 1 are connected. Here we can see that they are connected, so we return true. And for instance, whether 2 and 6 are connected. Here we see that there is no connection between them, so we actually say that they are not. Yeah, they are connected. I mean, for instance, between 6 and 3, whether they are connected or not, we see that there is no path between 6 and 3, so we say that they are not connected. So if we have a question how many connected components here, we can actually say that there are 2 connected components. So it's easily visually to see, but connected component is the number of vertices which are connected when there is a path or from every vertex to any other vertex in this graph. So I think it's understandable. So why it's useful? Let's actually make the problem larger. So for instance, if there are so many points, here we have thousands of points, and how to find the path connecting P and Q? So yeah, that's a challenging problem, and we can solve it in the algorithms which we'll cover today. Let's start from the modeling of the objects. So you remember we actually said that in order to model, in order to solve the problem, we have to first model it. And applications involve manipulating objects of all types. So pixels in a digital photo, so we have a digital photo, have a lot of information over there, and we model it using pixels. Computers in a network, so we actually say that the network is just a connection of computers. We can model a social network as your friends, transistors in computer chip, and so on. And when programming, convenient to name objects 0 to n-1. So when you have an object, for instance, you have a computer, you have n computers, so each computer will have an ID from 0 to n-1. So use integers as array index. So you know what this array is, just a collection of elements, and each of the element has an index, and you have to use integers as array index. And suppress details not relevant to union find. Can use symbol table to translate from site names to integers. So what's the point of abstraction and modeling the objects is to suppress details which are not relevant to union find. So if these are computers, you need to know only their IDs but not some extra information about the computer. So let's move on. How to model the connections. We assume is connected to is an equivalence relation. So reflexive, if P is connected to P, then it means that P is also connected to P. So it's actually about discrete mathematics, and I don't think that's so important, but let's actually consider this symmetric. If P is connected to Q, then Q is connected to P. So it's understandable. So for instance, here if 1 is connected to 4, then 4 is connected to 1. So it's bidirectional. And transitive is if P is connected to Q and Q is connected to R, then P is connected to R. So for instance, if 1 is connected to 4 and 4 is connected to 5, then 1 is connected to 5. What is connected component, as we said, is a maximum set of objects that are mutually connected. So how many connected components we have here is 3. It's very easy to recognize. Let's move on. How to implement these operations of union and find. Find is in which component is object P. So for instance, if there are 3 connected components of 0, at what connected component is 0 here? It's in the first connected component. Connected objects P and Q in the same component, it's easy to see, and union replace components containing objects P and Q with a union. So for instance, we say we know 2 components and how to actually union them into one. So for instance, here we have to union 2 and 5, and we do some connection between 2 and 5, and we reduce the number of connected components from 3 to 2, given that we made the operation of union. And it's all philosophy how we do union we'll cover in the next slides. For now, let's move on. So what is union find data type API? API is just an abstraction which we use some main operations of union find. Here we see that the main operations is union, find, and connected. And design efficient data structure for union, find. How to do that? We have to have number of objects n, which can be huge. Number of operations also can be huge. And union and find operation may be intermixed. So it's very difficult to select the algorithm which is suited in this case, but let's move on and see how we can do this. First of all, let's see the function of connected to check whether two objects P and Q are connected or not. So we find is actually identifies the component to what the P is belonged to, and if P and Q are in the same component, then they are connected. So it's easy one-line implementation. And here we see how dynamic connectivity client is performing. So in the code, we read some input data in the integer format. We initialize union find object with n parameter, and while stdin is not empty, we read P and Q and check whether they are connected or not. If they are not connected, we union them. Yes, it's all about the union operations. And after that, we print a pair. So for this video, let's cover for now quick find how does it work. It's difficult for newbies to understand how this algorithm works because it's easy, but actually we see it in some hierarchical form, and for people it might be difficult to understand, but here we will try to simplify this process. And the quick find, eager approach, data structure, array ID of length n. So first of all, we have to actually have data structure which for each object there will be some index associated to that. And interpretation ID of P is the ID of the component containing P. So here the ID of the component containing P. So 0 is belonging to the zeros component, 1 is belonging to the ones component, 3 is belonging to the eights component. So here we see that in the cells which are equal to 0, they're in the same component, in the cells which are equal to 1, they're in the same components, and the same for 8. So there are 3 connected components. It's easy, yes, it's an eager approach. And now let's define it in a little bit in a more depth. Here we have integer array ID of length n. N is the number of components. Interpretation, it's covered, and now in order to implement the operation of find, we have to answer the question, what is the ID of P? What is a component of P? It's actually easy, we just return ID of P and connected. Do and P and Q have the same ID? If they are, if the values, if the IDs are equal, then they are connected. But how to do this union? To merge components containing P and Q, change all entries whose ID equals ID P to ID Q. So for instance, if we connect 0 and 1, and then we change all the entries which are equal to 0 to 1, and doing that, we actually do the union operation. Let's see how it works in code. Yeah, it's also understandable, but the thing which we didn't cover is union. To do the union, we just find the IDs of these two objects which we want to connect, and we substitute the IDs, the values of ID for the QID. It's the same as we did with 0 and 1 component. So what's the problem? It's all about the cost model. So if you remember, we actually said we have to question whether our algorithm is fast or not. And here we see that in order to initialize quick find, we have to perform n operations in order to fill in the array. In order to use the find operations, only one operation, okay, connected one operation, and union is n operation because we have to change all the entries which are equal to some component to another component. So here we see that union is too expensive. It takes n to the power of 2 array accesses to process a sequence of n union operations on n objects. because for each union we actually do the two find operations, and then we substitute of the values of the first object to another object, as we actually said about the 0 and 1. So I think it's understandable, because if the union takes n operations, and n unions will take n square operations, so that's why it's quick find. Find operation is quick, but not the union. And what's the problem of quadratic algorithms? That it's the problem that they do not scale. So what if we have not 10 objects but 10 millions objects, and the actually running time and how it increases, it will look like an exponential one. It's quadratic, yes, but it's very, very, very fast in comparison, for instance, in linear arithmetic or linear. So there is a reason to improve this. Why not? So yeah. So thank you everyone for attention. In the next lecture we'll cover quick union. So if we sacrifice the find operation, how we can make the union operation a little bit faster, and how to improve all this. Maybe we'll come up with some better algorithms how to handle that. Maybe both union and find will be optimized. And if that's so, it would be very beautiful. And whether we can actually optimize it even more, we'll answer to this question, and some application of that will be covered. So stay tuned.